Hello and welcome to this DuPont Nomex Energy Solutions webinar. My name is Rich North and I'm your host from Global Spec. I would like to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading DuPont Presentation in the upper left is the primary window for today's webinar. You should be seeing the welcome slide there right now. Just to the right of the main presentation window is the speaker bio window with background information on today's presenter, Rick Merrick. Now just below that is the Q&A window, and at any time during the presentation, you can enter a question into the box in the lower section of the Q&A window and click Submit. Your question will be placed in the queue for Rick to address when we get to the Q&A session. Now if you look to the bottom of your screen, you'll see 8 buttons. The first 3 either minimize or restore the 3 windows we've already talked about. The others allow you to share this webinar with colleagues, take a survey to provide feedback to our presenter. You can access resources, and lastly do a little troubleshooting like running the system test or consulting the FAQ document. The button second to the right is the volume control for the webinar. It is probably best to leave that button alone and adjust your volume using the controls you are familiar with on your own system. If you can't remember what a particular button does, just hover your mouse button over it and a tooltip will appear with a description of the button's function. Now to get this webinar started, here's your DuPont moderator, Gary Burnett.
Hello, and thank you for joining us for this exclusive webinar on new standards for the modern transformer. This presentation will discuss the new document soon to be published that will standardize high-temperature liquid-immersed transformers and the recently published standard that defines the test procedures for determining the thermal class of an insulation system in a liquid dielectric medium. Rick's talk will focus on transformer standards continue to mature and evolve, high-temperature liquid-filled transformers are standardized, family of insulation temperature classes are defined similar to dry-type transformers, and procedures to determine the thermal class of a system are defined. Now I say we let Rick take this presentation over. Rick?
Hello, my name is Rick Merrick and I work for the DuPont Energy Solutions business. As many of you know, I am an active member of the IEEE and participate in many of the working groups addressing standards for the electrical power transformer industry. For some time now, liquid-immersed transformers have received much attention due to an active global interest in high-temperature liquid-immersed transformer applications. The result is a new IEEE standard for these transformers. In today's presentation, we will first set the stage for the new standard that governs high-temperature liquid-immersed transformers. Key aspects of the new document will be explored, and then we will see how the insulation system standard, revised a few years ago, complements the new document by defining procedures necessary to establish new temperature classes. Finally, we will look at what standards work remains to complete the whole picture, along with some photo examples of typical applications. High temperature use really isn't new for the liquid immersed transformer. As far back as the early 70s, high-speed trains in Europe were designed using lightweight traction transformers, made possible by high temperature technology. Around this time, Westinghouse also developed a high temperature distribution transformer, although it never came to production due to high cost. Both of these applications used silicone liquid due to its very stable performance at high temperatures. In the 1980s, DuPont and Weidmann collaborated to develop a family of Aramid Nomex brand pressboard products similar to the Weidmann cellulose products. These products opened the door to power transformer repair applications, especially when increased power was necessary. High power density mobile transformers also became available to meet the increasing needs for temporary replacement power. All of these applications took advantage of windings operating at high temperatures, but still used mineral oil operating at normal temperatures. the hybrid transformer was born. In traction transformer applications, synthetic esters were first used during this time. The 1990s saw increased interest in weight-restricted applications, borrowed from the success of the mobile transformer applications. The Korean utility, KEPCO, needed replacement 40 MVA units for substations stranded by bridge weight limits that were reduced after one collapsed. A choice was necessary: either 3 single-phase units or 1 3-phase operating at high temperature. KEPCO also was looking for a lighter weight, 150 kVA pole-mounted transformer to avoid the cost of the necessary switch to twin poles and a platform. In China, the kVA rating of trackside rectifier transformers was reduced using the overload capacity of a high-temperature design, thereby reducing the tax assessed based on kVA rating. Applications have continued to expand over the last 10 years. Natural ester has become more popular and is now being used in high-temperature applications such as wind turbine step-up transformers. The applications have also shifted to a point-use application for specific problem solving. For example, high-temperature insulation on the wire only for power transformers is used for life extension for severe duty applications. High-temperature insulation is also used on lead exits and core insulation to prevent hotspot issues and gassing. Technology normally precedes the documentation of standard development, and it was no different here. The first high-temperature document was published as IEEE 1276 in 1997 after the working group developed a very comprehensive background paper. Using 1276 as a reference, an IEC technical specification was first published in 2004 and subsequently revised in 2009. It is currently in revision now to upgrade to an international standard with a completion target date of 2013. All of this leads to the main topic of this presentation, a new standard for high-temperature liquid immersed transformers to be published by the end of this year. The new document will be a standard and not a guide like the earlier documents. It is intended to provide limits and structure for development in the design, testing, and application of high-temperature liquid immersed transformers. Note that this standard applies only if high-temperature insulation is used and the unit is operated at temperatures that exceed that of a normal transformer, as defined in IEEE C5712.00, which is the base standard for liquid immersed transformers. This means that C5712.00 still governs transformers that operate at normal temperatures even if they use high-temperature insulation. The definition of 3 key terms was necessary for this document. The first term is reference temperature. The standard temperature to which calculations and measurement are referred shall be defined as 20 degrees C plus the base rated average winding rise. For multiple winding transformers that have more than one base rated average winding rise, the highest average winding rise shall be used to determine the reference temperature. This definition was actually added recently to IEEE C5712.80 in the last revision. The word conventional has a special meaning in this document. It is a description applied to temperature rise limits, insulation materials, or insulation systems operating at temperatures within the normal thermal limits of C5712.00. And just to be clear, the thermal limits for the winding are defined as 65 degrees C average temperature rise, 80 degrees C hottest spot temperature rise, and 110 degrees C hottest spot temperature. The temperature limit for the insulating liquid is defined as 65 degrees C top oil temperature rise. Finally, high temperature is defined. A description applied to temperature rise limits, insulation materials, or insulation systems operating at higher temperatures than conventional. The new standard also defines 3 insulation systems: conventional, high temperature, and hybrid. Hybrid has 2 variations: full hybrid and mixed hybrid. The next few slides will visually describe these 3 insulation systems. Conventional and high temperature are the simplest systems, and for clarity, a power transformer pictorial is used. Conventional is just the standard transformer described by C5712.00. It is composed of mostly cellulose insulation products in an insulating liquid that is usually mineral oil, but could also be one of the many mineral oil variants, an ester liquid, or a silicone liquid. The sketch reflects the rather uniform thermal capability of all of the components of this system. The same uniform sketch applies to the high-temperature insulation system as well, since nearly all of the components, including the liquid, operate at temperatures above that of the conventional transformer. The full hybrid insulation system uses a combination of conventional and high-temperature insulation, but the high temperature is only used where conventional temperatures are exceeded, and the key location is the conductor insulation, as highlighted in the sketch. Radial and axial spacers touching the conductor are also changed to high-temperature insulation. Depending on the design, other components may also require high-temperature materials, such as disc angle rings. However, the static rings, main gap angle rings, and cylinders all remain conventional materials, even though the unit operates at higher than conventional temperature rise and hottest spot temperatures. The insulating liquid may be any type, but the operating temperature is conventional. Mixed hybrid insulation systems are problem solvers in that only enough high-temperature insulation is used necessary to protect a hotspot location. Most of the insulation is conventional, and the unit operates at conventional temperatures for the liquid and for the average winding rise. However, one or more hotspot locations, including the hottest spot, exceed conventional temperatures. So as an example, the conductor insulation could be high temperature for a portion of the windings. In a similar fashion, only a portion of the radial axial spacers and the disc angle ring would also use high temperature insulation. Also, since this is a targeted approach, it could be that only one winding could be affected. In a major departure from the base liquid immersed transformer standards, the new standard defines multiple insulation system thermal classes. C5712.00 only recognizes thermally upgraded insulation and mineral oil, or the equivalent. Once temperature limits are removed, though, the door opens for multiple systems with different thermal capabilities. The new thermal classes are defined in order to structure the development of these new insulation systems in an orderly fashion. The concept is very similar to that of dry-type transformers and motors, which have functioned very well for many decades of use and development. As you can see by this table, the relationship of the hottest spot temperature to the maximum system temperature is also defined as 10 degrees less than the thermal class temperature. Using these insulation system thermal classes, a family of thermal temperature rise limits can be developed as shown in this chart. Note that for hybrid insulation systems, the top liquid rise never exceeds the conventional liquid rise of 65 degrees C. The maximum hottest spot temperature is just the sum of the hottest spot rise and the average ambient temperature of 30 degrees C. For comparison purposes, the conventional temperatures are shown in the second column. The key important temperatures begin with the minimum thermal class for the high temperature insulation in the system. This thermal class then sets the limits for the average winding rise, the hottest spot winding rise, and the maximum hottest spot temperature for normal life. The mixed system compared to the conventional is only different for the hottest spot rise and maximum hottest spot temperature, which are 10 degrees higher. The full hybrid with the same 130 thermal class differs from the mixed by also allowing a 10 degree higher average winding rise as well. With a 140 thermal class insulation system, an additional 10 degrees C is available for the average winding rise, hottest spot winding rise, and maximum hottest spot temperature. A 95 degrees C average winding rise is the limit for a 155 thermal class insulation system. A 145 degrees C is the maximum hottest spot temperature with a 115 degrees C hottest spot temperature rise. A similar pattern is followed for the high temperature insulation system thermal limits. Ester liquids have a maximum top liquid rise of 90 degrees C with a 115 degrees C limit for silicone. 4 different thermal classes are shown for each liquid. The average winding temperature rises are then 75, 85, 95, and 115. The maximum hottest spot temperature for each system is 10 degrees C less than the thermal class temperature. Several years ago, IEEE C57-100 was revised to clarify and expand the procedures. This is the document that defines the procedures for determining the thermal index from which the thermal class is derived. In this case, the thermal index is the projected point on the Arrhenius life curve which intersects at 180,000 hours of life. The associated temperature is the thermal index, which corresponds to the expected life in a 30 degrees C average ambient temperature. The thermal class is then 10 degrees higher, corresponding to the maximum 40 degrees C ambient temperature in which the system is capable of operating. The 3 tests defined in this document are the functional life test, commonly known as the Lockheed test, the sealed tube test, and the newest addition, the dual temperature test. This is a photo of the test setup for the Lockheed test. It typically uses completed pole-type transformers, and end of life is signaled by dielectric failure. Since this is an accelerated functional life test, at least 3 temperatures selected well above normal operating temperatures are tested in order to draw an Arrhenius curve. This is a closed cell used in the sealed tube test. It is a single temperature test where all materials, including the liquid, are placed in the cell, which is then placed in an oven and maintained at the test temperature. Again, 3 elevated temperatures are selected to accelerate the aging. This test was originally intended to evaluate substitute materials and has been modified to allow determination of a system capability by changing the determination of the end of life criteria and by extending the extrapolation of the curve to 180,000 hours from the original 65,000 hours. Specific proportions of insulation, both paper and board, to the liquid are also specified. A pressure relief valve is specified to maintain normal transformer pressures. The sealed tube test is the easiest insulation system accelerated life test to perform. However, its application to high temperature materials is questionable, since the liquid sees the high temperatures and is certainly damaged. It is particularly unsuitable for systems with components that have broadly dissimilar thermal capabilities, such as Nomex and mineral oil. The dual temperature test was originally developed by Bill McNutt after retiring from GE as a way to evaluate high temperature insulations in mineral oil. The procedure is an improved version of the sealed tube test that is more versatile, although it is focused only on the wire insulation. While the liquid is maintained at a constant temperature of 115 degrees C, the insulation on the conductor can be operated at much higher temperatures in the range of 150 to 250 degrees C. Since end of life is based on tensile retention, the procedure should be suitable for most materials. Specific proportions of insulation, both paper and board, to the liquid are specified for this test as well. The oil preservation system is duplicated in this procedure and may include a nitrogen blanket. The photo on the left shows the insulated conductor blanketed by press board. Current is then driven through the wire loop by the current transformers shown in the photo on the right, maintaining a constant temperature which is controlled by thermocouples touching the wire insulation. The cylinders are filled with the liquid and the airspace is purged and filled with nitrogen, maintained under positive pressure. A cross-section of the cell is shown here. Thermocouples attached to the wire under the insulation maintain the selected insulation temperature, and thermocouples in the liquid maintain the different liquid temperature. But the standards work is not yet complete. Evaluation procedures are still needed to determine the thermal class of a liquid and the thermal class of a specific insulation material. There is still some confusion in the C57-100 document. Since the dual temperature test only tests the conductor insulation, is it a system test or a material test? Is the sealed tube test really a system test as described in C57-100, or is it really a material test? Additional clarification is needed. Test procedures are also needed for enameled wire and for press board. And now for the commercial. I think most people are familiar with the DuPont Nomex products used for components and for wire insulation. Nomex has been available in paper, crepe, and board for liquid immersed applications for many years, but more recently an improved wire wrap was developed specifically for liquid immersed power transformers. Finally, let's look at some of the typical applications. Here are examples of distribution type transformers with many variations in the windings and the core and coil assemblies. Traction transformer applications have been some of the longest running examples of high temperature applications. The horizontally mounted forced liquid cooled units are very specialized. There are many variations in applications for power transformers. Here are some of the variations in the active part where the coils are mostly disc wound. Mobile transformers and substations are very common, but substations and trackside rectifier transformers have also seen good applications for high-temperature insulation systems. Even commercially successful pole-type transformers and pad-mounted transformers have been developed for high-temperature applications. For more than 10 years, high-temperature liquid immersed transformers have been used in wind turbine step-up transformers, and they are becoming even more important now for offshore wind farms, where space and weight are a premium. Thank you for your time and attention for today's presentation.
Rick, thank you for that insightful presentation. And now let's get to our question and answers. Again, if we don't get to your question today, don't worry. We'll have an answer for you within 24 hours. The complete question and answer transcript, including answers we did not have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into on-demand mode. So why don't we begin with our very first question. Rick, the first question that came in asks, are there any standards for the oil-filled motors?
To be honest with you, I doubt it, but I don't know that for sure. I have never heard of an oil-filled motor standard, and they would be in a different group from the transformers anyway.
Thank you, Rick. Here's another question that's come in. Are you concerned, Rick, about the dielectric strength of the oil at the interface between the 150 degree C winding? Won't the oil create gas bubbles?
Well, this will be a function of the gas saturated in the oil and also the moisture in the material. So a well-dried transformer that is maintained in a dried condition should not see bubbling conditions.
Okay. Another question has come in. Is a three-phase symmetric short circuit current the same as a three-phase short circuit current provided by the transformer?
Well, if I interpret the question correctly, I believe the question is, are high-temperature transformers, do they meet the same short-circuit requirements as conventional? And the answer would be yes.
All righty. Question has come in. I have a customer that wants to move up in class, currently using Kraft Mylar, and wondered if a Monex Mylar Nomex will work, like using Nomex 410 in a laminate.
Laminates are generally not recommended for use in liquid-filled transformers. And even Mylar would not be recommended due to hydrolytic instability. So I would avoid laminates completely in the liquid-filled. Part of the issue, too, would be the high potential for trapping air between the laminate when it is created.
All righty. Thanks, Rick. Question is asking, have you ever experienced EnviroGuard fluid holding moisture in large substation-style transformers?
I believe EnviroTemp, I believe, is maybe what is meant. And yes, it does. It does retain much more moisture than conventional mineral oil, but tests have shown that this is not necessarily an issue. Magnitude, of course, is always the question.
All righty, great. Thank you, Rick. One member of our audience is asking, is there any impact on DGA analysis of the oil with these higher temperatures?
Well, really, I guess the question is whether you can use DGA for this type of transformer, since there are different materials involved. Generally, the answer would be yes. You would look for the same characteristics. The high-temperature materials typically do not generate moisture as they degrade compared to the cellulose that does. But the DGA analysis would remain very much the same, especially in a hybrid type transformer. In looking at the high temperature transformers, though, you have a completely different set of materials, and likely an ester or a silicone, and guidelines have not been developed yet for this type of application.
Thank you, Rick. Here's one for you. Would you allow for higher gas concentrations in transformers with a tap changer, such as in foundries? And if you would, how much higher?
I don't know the answer to that one. To be honest, tap switches are not really part of my expertise. Sorry.
Not a problem. Someone from our audience is asking, apart from Nomex and Kapton, are there any other materials that could be used for high-temperature liquid immersed transformers?
Well, there aren't very many. That is for sure. None others that I can think of. In some cases, polyester glass is acceptable in some mechanical applications, but not a good choice for areas that see dielectric stress. The document, as long as the question's been asked, keep in mind that this document was intended to kind of set the stage for development of high temperature materials. And it is hoped that this would provide a structure for the development rather than just random process. And that is why multiple temperature classes have been established, even though they don't yet exist.
Thanks, Rick. Someone has asked us, have there been any short circuit tests of medium power transformers with Nomex high temperature windings? If there have been, do you know where and when?
I do not know. To give you a short answer, I'm not sure whether tests have been performed on these units. I suspect they have, but I don't know that for sure.
Okay. A question has come in. What is the most common current and future applications of high temp and hybrid transformers?
Well, the most common hybrid is, of course, the mobile transformer. These units have been manufactured since the 80s and have been around for many, many years. It's just a very classic application of looking for maximum power for a given weight. So you're looking for a small size, large capacity transformer. The high temperature transformers, we have seen a very strong interest in Europe in the wind turbine transformer application. And very specifically for applications where the step-up transformer is located within the pedestal, where they're looking for small size. It's also very good application for offshore wind turbine applications when you're looking for a situation where the unit needs to be protected from the environment.
All righty. Someone has asked, Rick, with these new materials, are there any known tests of the oil to determine insulation remaining life?
Oil is a difficult topic here. Remaining life means that you have some given way to determine what end of life is, and I'm not sure that that is so well defined. There are no Arrhenius curves, for example, for the different liquids, and keep in mind that even the temperatures that are used within this document are temperatures that have been estimated to be acceptable, but there are no real tests. Now, mineral oil, you could look at several different categories of gassing or of the quality of the oil to determine the end of life, but I'm not sure. I'm not an oil expert either, so I'm not sure that that is so well defined.
Thanks, Rick. How does dielectric strength of Nomex compare to conventional materials in a liquid-filled environment?
Well, we find that the Nomex insulation has approximately the same dielectric strength as conventional kraft papers, both in the board and in the paper materials. So, of course, you find many variations just in the kraft paper alone, so it's difficult to, unless you were to compare one to another, but in general, most people start out using the same design rules for the Nomex that they were accustomed to using for their cellulose applications.
A gentleman has asked us, the wire wrap you spoke about, is it a replacement to the normal kraft, I guess kraft paper, or thermally upgraded paper insulation for power transformers?
I'm not sure. Say that again, please.
Sure. The wire wrap you spoke about, is it a replacement to the normal kraft or thermally upgraded paper insulation for power transformers?
Well, the wire wrap mentioned it was actually Nomex, and it would be, yes, very different from the kraft and a higher temperature capability.
All righty. Here's one for you. Can high temperature transformers be used to satisfy longer life specification requirements under normal temperatures? So let's say 60-year spec for a new nuclear power plant as an example.
Well, yes. Higher temperature application means that you have a given life at that temperature. So if you operate at a lower temperature, the life is extended, and depending on the particular application, you can extend the life to a very long period of time. So 60 years was given in the example. The assumed life of a standard transformer is 20 years. So you're looking for a 3 times multiplier, and using high temperature could possibly give you that extra length of life without changing the design. You would, of course, have to do an analysis, but the concept is correct. Higher temperature insulation at normal temperature gives you longer life.
Great. Here's a question for you. What's the recommended AC stress level to avoid partial discharge in the Nomex material?
Well, again, our recommendation is that you use the same guidelines for Nomex insulation that you would use for the cellulose corresponding product.
Okay. A member of our audience has asked, does moisture affect Nomex the same way it might craft paper?
Well, no, it doesn't. Actually, Nomex will retain less moisture than cellulose in open air. And in liquid-filled applications, moisture will attack the cellulose much more than the Nomex. So moisture is always a bad actor in any case in a liquid-filled transformer, but it will have a larger effect on the cellulose than the Nomex.
Here's another one. If you want to establish compatibility between insulation materials, magnet wires, and a liquid insulation at high temperatures, what kind of tests do you suggest to perform, and what might the results look like?
Long question. Say it again, please.
Sure. If you want to establish compatibility between insulation materials, magnet wires, and a liquid insulation at high temperatures, what kind of test do you suggest to perform, and what might you expect results-wise?
Well, I think probably the best test is what's known as the sealed tube test. It has a long history, and in the last few years, the test has been modified a bit. It is now actually defined in IEEE C57.100, and using this test procedure, you could determine both compatibility and the life of the material. Now there's also an ASTM standard, and I don't remember exactly the number, but there is one that is very specifically for only compatibility. Now, by magnet wire, that's unclear. I'm assuming that the reference is to the enamel, and enamel in the different liquids can be an issue at elevated temperatures. So we have to be careful there, because many of the enamels are not suitable for high temperature application in liquid-filled transformers.
Great answer, Rick. Here's one for you. When referring to the C57.12.00 3-point aging test, what's the highest temperature of the oil that will still yield?
Well, the 3-point test, the reference must be to C57.100 because 12.00 doesn't really define the test procedure, and there are two test procedures in 100. One is the dual temperature, and in this dual temperature test, the recommended temperature, I believe, is 115, which is held constant while the other insulation is operated at an elevated temperature.
All righty. Here's a new question that's come in. From the dielectric point of view, what is the best insulation liquid? Mineral oil, ester liquids, or silicone?
Well, I think clearly mineral oil has the longest track record, and I think that's probably still the number one choice. ester would be better than silicone. So if I were to rank them, I would make it mineral oil, ester, and silicone, and that's just my opinion.
All righty. Here's a question about wire wrap. For determining thermal class of a wire wrap at the end of thermal aging, either by seal tube or dual temperature, what is measured, dielectric or tensile strength?
Well, tensile strength is the preferred method. You could also use DP if it's a cellulose product. Dielectric is a difficult one because the dielectric strength seems to hold all the way to nearly total degradation. So it's not necessarily a very good way to measure end of life, although it is the only practical method for an enamel. So tensile strength is the choice, and it does allow the use of this end-of-life measure across a large range of different products. To give an example, DP cannot be measured on Nomex. So while DP is favored very much for cellulose products, the test, in order to be universal, would be better with the tensile test.
All righty, thanks. Here's an interesting question for you. How is the moisture balance between Nomex and insulation oils compared to conventional paper and insulation oils?
Actually, they are very similar, and we have recently done some tests to develop the moisture equilibrium curves, and they can be supplied on request. There's actually a paper that one of my colleagues wrote, I believe it was within the last year, and makes a comparison between the cellulose and Nomex products. But my recollection was that they were similar.
Here's another question concerning oil immersed power transformers. One of our listeners asks, would you please elaborate more about Nomex applications for oil immersed power transformers?
Well, of course we talked about the mobile transformers. The last section of the presentation showed a number of typical examples. Trackside rectifier transformers, for example, would be a good application, largely because they see very severe loads and then long periods of idle load conditions. So the large changes make a high temperature transformer a good application. We talked about the wind turbine transformers. We see that there are a couple of places around the world where lighter pole type transformers have been used to advantage. The typical application is that if you have to upgrade a transformer, then you may have to go to two poles because the larger transformer is too large for a single pole. And this illustrates a really good general statement about high temperature as well, and that is that the transformer is rarely cheaper than the conventional in an application like this, but in this case, by avoiding another set of poles and a platform, the overall installation would be less expensive, even though the transformer itself might be more expensive.
Great. Here's another one that's come in for us. This one asks if you wouldn't mind comparing tensile strength between Nomex and kraft paper.
Nomex tends to be a little higher in tensile strength than conventional kraft, but we have to be careful. It depends on which product you are comparing to. Some of the newer wire insulations have very good tensile and very good elongation as well. But in general, Nomex has an edge on tensile strength over cellulose.
And along those same lines, a question just came in asking, what will be the temperature class, I would think. What will be the temperature class of kraft paper and Nomex for high temperature liquid immersed transformers?
Well, you would want to look at them individually. Of course, the thermally upgraded kraft paper is a 120 class, and the standard for determining the temperature class of these systems has changed, C57-100. So we do not have a number yet for Nomex. After a good deal over a year of testing, we still have not even reached 50% of its tensile strength yet. So it will be a while before we have a final number on Nomex.
Okay, here's one a little bit different question, and this one is asking for your opinion, Rick. Does the enamel on the copper conductor make a difference in oil-filled transformers?
Does it make a difference? Well, enamel has been used for many years. It's a very good product. It may not be suitable for high-temperature application, however, and it needs to be carefully checked before it's used. Some enamels appear to be suitable, but the more conventional, lower-temperature ones are not.
Okay. Someone is asking about oil and mineral oil. The question is, what is the difference between the EnviroTemp FR3 oil versus regular mineral oil? Do you recommend the FR3 oil?
I don't recommend anything. That would be up to the user's choice. The EnviroTemp is a good product, and it has some improved characteristics over mineral oil. One of them being a very high fire point, making it suitable for indoor application, and mineral oil is not. So I don't know that you can just make a broad general statement. You have to look at your application and then decide. The typical ester, FR3, is more expensive than mineral oil. So it depends on your cost issues as well. So very difficult and no general answer to that question.
Here's a question about dry type application. how can we determine if the insulation is under overheating conditions or not? And this is related to dry type transformer applications.
That's I don't know that I can answer that because I would need more information. I can't really answer specifically.
Here's another one for you. This one asks, what's the most common thickness of Nomex used for wire wrap?
2 mil is by far the most popular thickness. And there are 2 versions, actually. The T410 is the most common and the one that has been around the longest. And it's used both for liquid and dry type applications. But there's also a newer product, a T926, that offers some improved characteristics, and it is focused very specifically on liquid filled and not recommended for dry type.
Okay. A question has come in, Rick. Do you have any experience for an application on transformers with high primary voltage level transformers like 745 kV?
Well, one day 765 kV will be used for with Nomex, but so far the highest is 400 kV. I believe it was a 345 kV has been the highest to date.
Okay. We're getting close to the end. Let me see if we've got a couple more questions for you. This one asks, are there any other fluids like, the spelling here is got me, is it PAQ or PAC? Are any other fluids like PAQ and new GTL mineral oils, have they been tested in the applications you've been talking about today?
I don't recognize that term. Let's go on to the next.
Sure. Is water a byproduct of Nomex insulation aging in the same way and degree as it's a byproduct of Kraft paper-based insulation systems?
Well, there's good news and bad news. The maybe good news is that no, water is not a byproduct of Nomex as it degrades, but on the other hand, we have not found a tracer either. So I would have to say no. No help here.
Well, Rick, unfortunately, we're going to have to wrap up the webinar. We've run out of time, so I just want to thank Rick, our Applications Research Associate at DuPont. Thank you for spending the time with us today.